Alright, I'll get that. Alright, so I've got some function on the interval a to b, and I want to find the area. What do we do? What do we do? How would you go about finding that?
Split it up with rectangles.
Okay, that's one way, right? We could break this up into rectangles. We could break it up into, what was the other shape? Trapezoids, okay? But as a calculus student, what are you going to do? You just get to like fast forward, past all the stuff that Riemann had to do. What would you do if you wanted to find the area?
Calculator.
Right now, we would plug this into our calculator. But what would you put into the calculator, Brian? If I wanted all this area, what would you plug into the calculator? Here's some function f of x. What would you do?
The sign called?
The integral sign?
Yeah, the integral sign, and then a to b.
From a to b, the a and the b, these are, what was the fancy word for this? There's a fancy word for these things.
Integrand.
Not the integrand. Oh, so sad. And everyone's just like, don't call on me. If I don't get volunteers, I go for victims. You know it. Okay, if I'm going from a to b, these are your limits of integration.
Oh, there you go.
Limits of integration. So I want to integrate from a to b. What is it that I'm integrating? F of x. Whatever my function is. And the last part is this dx. The way that I would read it, it's the definite integral of f of x from a to b with respect to x. What it really means, though, is the bounded area. It is the area bounded by four things. Those four things, the x-axis is one of those. The function is the second thing. Victoria, what are the other things? We're bounded by the x-axis. We're bounded by the function. What are the other things?
Where x equals n or x equals b.
The vertical lines, x equals a, x equals b, right? There is going to come a time where we're going to do this without the calculator. But for right now, the most part, if it is not a friendly area, you're just going to say, oh, let me go plug this into my calculator and I'm done. What I want you to get in your notes, though, is what's Riemann's idea here? Back in the 1840s, no computer, no calculator, what did he do? Somebody get me started and then you're frozen. What would he do?
We had to make, we would find using equation, then bounded by those A and B,
Yeah.
and then make multiple rectangles.
That's the piece I wanted to start with. We'd start with rectangles, right? How many rectangles?
As many as
As
you want.
many.
As many as you want. Maybe it was 5, maybe it was 10. So I'm just going to say n rectangles. So if I start with n rectangles of, for convenience, let's say equal width, then I'm going to say, oh, you want me to go from A to B, and I'm going to make all these little slices. And the way that I figure out the width of each rectangle, it's b minus a divided by n. It's the length of the interval. This is the same a and b that we're talking about over there, divided by the number of rectangles. Wherever I'm making these cuts, we're going to call that the partition. So we're going to break up this interval using a partition. There it is. And if this first guy over here is what I'm going to call A, then this endpoint over here is going to be A plus delta x. It's A plus however far you tell me to go. And then this next endpoint over here is going to be A plus 2 delta x. And the next one after that is going to be A plus 3 delta x. It is important for right now that those rectangles have the same width. Okay. This is not always going to be true, but for right now, Jose, all equal width. Now, we've got some choices to make. Which method do I want to use? Which method could I use?
Doesn't matter.
What are the options?
Left
Left endpoint method,
right.
the right endpoint method,
Midpoint.
midpoint method, trapezoids. Okay, let's talk about the right endpoint method. If I'm going to do the right endpoint method, which I'm just going to abbreviate as REM, one of my favorite groups, I'm going to go on this first interval from A to A plus delta x, and we're doing the right endpoint method, so I take the right endpoint and I say, oh, you tell me to go up, go over, go down. That's that first rectangle. And so if I want to find the area of the first rectangle, I take the width. How wide is that?
Delta X.
That width is delta x. And I need to multiply this by something to get area, right? It's the width times the height. So what's the height? How are we determining the height? The width is delta x. I'm using the right endpoint method. That's the clue.
So F of
It's f of a plus delta x, and that gets you the area of the first rectangle. Second rectangle, I'm going from a plus delta x to a plus 2 delta x. I'm going to go to the right, up, over, down. Second one. Victoria, what's the area for that second rectangle?
Delta x times f of 2, f of a plus 2 delta x.
A plus 2 delta x, right? And I'm going to add those two together. And check back if I wanted the area of the third one, what's it going to be?
Delta x times f times a plus 3 delta x.
3 times delta x. And I'm going to keep going with this process forever until I hit the nth rectangle. And that nth rectangle, that's this guy over here. I'm just going to call it n. The endpoint that I use is b, because it's the right endpoint method. I'm going to choose to write this in a weird way, though. I'm going to write this as delta x times f of a plus delta x n times. Now, does that actually work? Well, delta x is b minus a divided by n. So imagine that you had written a plus delta a plus b minus a over n times n. The n's are going to cancel out. A plus b minus a, the a's are going to cancel out, and I get f of b, and all is good. Okay? Fancier notation than where we started last week, but we're in week 2, so we can, our skills get to evolve. Big picture, is everybody okay?
Yeah.
So the new piece that I layered on Friday was to be able to collapse this down so that you're not writing each of these terms separately, but instead you get to pull them all together because you see a pattern. And that was sigma notation. So if I'm going to use sigma notation, and it's just another fancy way to write the same thing, I'm going to rely on the pattern here. And what's the pattern?
Delta x.
There's a delta x.
And then there's f of x or something.
Okay, there's
I mean, that
f of
was something.
stuff. Look at each of the terms. What's the pattern?
A
There's going to be an a.
plus
plus delta x times n.
A plus delta x, and here's where I want to be careful. I agree that they're all f evaluated at a plus a multiple of delta x. The important thing, and I think this is the part where maybe you guys get a little bit wonky,
isn't it
it's this index that you're going to use. It's your counter.
W?
So if this guy here is I
It's an
equals
11,
1,
that's fine.
then I start at 1. This guy over here is I equals 2. This guy over here is I equals 3. And I'm going to end over here at I is equal to n. So I'm going to go from I equals 1 to n, delta x, that's the width of each rectangle, f of a plus delta x times I. This guy over here represents the width. This guy over here represents the height. How's everybody doing? Victoria?
So for example, like I always like rating it the I instead of the n. It would make sense as long as I replace the i's with n, correct?
Wait. Yes. So I hear you saying if you said a plus delta x times n, that's fine. That means that n is your counter. And it's going to be confusing though because I'm going to talk about n being the number of rectangles.
Yeah.
This is the thing. This is the thing. This is what I care about. I care about everybody being able to get there. Now, the other day, I said, okay, let's call this A sub n to represent the area if there are n rectangles. Is this exactly the area? Anthony, why not? Why is it not exactly the area?
If we're using the right point method, wouldn't it be a underestimate?
Okay, I was afraid you were going to do that to me. The overestimate, underestimate isn't just because you did the right endpoint method. You have to describe what the function's doing.
because it's decreasing.
Okay, but it's not always decreasing. this function increases and it decreases.
But it has a point of inflection.
Okay, I see where you're going. You don't know enough about this function. I just sketched something to get us started. Okay, my question is this exact or estimate?
Estimate.
Estimate. Victoria, why estimate?
Oh, I was just gonna say, I don't quite remember the last part of the last class we had, but I remember that you said it was something about
That's your brain protecting itself, yeah?
Yeah, how it was the limit as whatever function we had approaching infinity, and that would give us the exact value.
Right. This can't be exact yet because look at all of your rectangles. All of your rectangles, you're going up to the curve on one side but not the other. Sometimes overestimate, sometimes underestimate. This is an estimate. It's stuck in the world of estimate. If you want to get exact, this was Riemann's brilliance. What did Riemann do to get to exact?
He used limits.
He used limits. What specific limit did he do?
Limit to infinity.
The limit to infinity. Okay, a little more specific than that because we're still here in the land of estimate. What goes to infinity?
X. Well, in terms of
The number of rectangles.
The number of rectangles goes to infinity.
Oh, I see.
Because if the number of rectangles goes off to infinity, then what happens to each rectangle? They get narrower, you get skinnier slices, and by getting skinnier slices, you're going to get less error. So the more rectangles, the better your approximation is. So to actually figure this out, what he would do is he'd say, oh, it's going to be the limit as n approaches infinity. I goes from 1 to n, delta x times f of a plus delta x times I. And this answer is the integral from a to b of f of x dx. That's the story. I care greatly that I should be able to give you any interval, any number of rectangles, and any method, left endpoint, right endpoint, midpoint, or trapezoid, and you can write out this particular sum. The bonus thing this year is, can you write this using sigma notation? And do you know that to get to a final answer, you have to take the limit as n approaches infinity? Getting here, I'm going to call it a day and say we're in a really good place. We're okay?
So this is with calculator.
This is what?
Is this with calculator?
With calculator, no. But this is the big picture. This is what Riemann was able to do. This is what you need to be able to do. And I think where I lost you guys on Friday was all the properties for sigma notation and things started moving all over the place, right? Like that's where things fell apart. I want to come back to that. I want to go over that, give you guys a second at bat. But really the important thing is, can you take that function over there, whatever the function is, whatever the intervals are, and set this up? That's the goal. So I'm going to give you guys 5 minutes. For this model problem that you've got over here, I've given you a function, I've given you intervals, I've given you a method. I want you to see, can you get to here? And then we'll talk and we'll come back to the place where I think I lost most of you guys on Friday. Okay? 5 minutes, help each other out. I'm going to pick up homework. Excellent. These are the things that we're due. Thank you. These are the things that we're due. Yeah. Thank you. And anybody that wants to make corrections to the swimming pool problem or anything else, Wednesday. Anything that you want to make corrections to, if you want to make corrections to this, I think that would be a good idea. Making corrections to this would be a good idea. Have you already made the corrections to that?
I would have had one left. That was
Okay.
So you only turn them in tomorrow? Both of them?
Yes, as long as I get them by Wednesday. At Wednesday, I'm going to call them off. Excellent. Nobody seems to be bothered by, well, no one seems to be bothered by maybe not knowing exactly what the graph looks like. So after a while, what you start to realize is the graph is just a crutch. It's there to help you out, but at the end of the day, I care about, can you tell me how wide each rectangle is? So each rectangle is going to have a width of 2 over n. This area, if I'm writing a sub n, I need width times, what's the first endpoint going to be? This might be the most important part. All right, we're going to go from 2 to 4. The width is 2 over n. When I make up my partition, when I chop up my interval, the first interval starts at 2 and ends at
2 plus 2.
2 plus 2 over n, right? Because this width over here, that delta x is 2 over n. And so the next endpoint is 2 plus 4 over n, and then it's going to be 2 plus 6 over n, dot, 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 and the last one better be 4, which is going to be 2 plus 2 over n times n. So this is 2 plus 2 over n plus 2 over n f of 2 plus 4 over n plus dot, 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 2 over n f of 2 plus n times 2 over n. If you and your smart particles need to write that out, great. If you can skip it because you're a really good pattern person, go straight for it. So what are the things? What are the things that are the same in each of these terms?
2 over n.
In each of the terms, I'm multiplying by 2 over n. And what was the significance of that 2 over n?
It was the change of, delta of x.
It's delta x, but what's the significance of it?
The width.
It's the width. And then all you have to do is take your width and multiply by your height. Well, how do I find the height for every single one of these rectangles?
2 plus 2 over n times
Right? You can write it as 2 plus 2 over n times I, and then your sum goes from 1 to n.
Where did you get the 2 from?
Where did I get this 2 from? Yeah, good question. Where's that 2 come from?
Isn't that
The first 2.
Isn't that A?
That's the A. That's your starting point. It might be helpful to do this partitioning of the intervals so that you can see it and be like, oh, start at 2, end at 4, move by 2 over n in each case. How many guys were able to come up with this is your, good Victoria, good Jose, okay. Did any of you guys skip this part and just go straight to here? If you can do that, great. But that's not the final answer. This is still estimate mode, right? So if I want to get to the actual true, hey, what is that definite integral of 2x squared minus 3x plus 3 dx from 2 to 4? Nathan, how do we go from this estimate to the final answer? Because we're here in estimate mode right now. I want to get the exact answer, and you might want to listen to this guy over here. I think he's trying to help you out. Okay, but what limit? There's a specific limit that I care about here.
The limit is n goes to infinity.
The limit is n goes to infinity because, what does that represent? If I say the limit as n approaches infinity, what you're really telling me is,
The area?
not the area, what you're saying is, get more rectangles. More rectangles means a better answer. So if you're able to get here truly, not just to make you guys feel better about yourselves, done, mission accomplished. We've made it to where I want to go to. But because you guys are also super smart, I want to go further. Okay, this is where I started to break you guys on Friday. Don't let me break you. Okay, so let's do it. Let's go big brain. Let's make Rogelio regret the fact that he's skipping school today.
I'm gonna laugh when he's like, oh yeah, I actually understood that last word.
All right.
You hear that, Roger? You hear that, Roger? You're gonna regret this day.
All right. Does anybody have any questions getting up to that part? If there's any questions, now is the time to ask. Brian.
Wait, if I equals 1,
Oh, no.
I love your thought there. If I is equal to 1, does this give me this term right here?
Yeah.
Right, this is like the mental check I'm going to go through. If I is equal to 1, 2 over n times f of 2 plus 2 over n. Check. The other one I'm going to check, I'm going to check at I equals n, because that's the tricky one. I is equal to n. 2 over n times f of 2 plus 2 over n times. 2 over n times n is 2. 2 plus 2 is 4. I ended in the right place. What's that?
For 2 plus 2 n times n, wouldn't that be an variable instead of n?
No, because we're talking about the nth rectangle, the final rectangle. Right, this is your first rectangle, your second, your third, your fourth, the last one.
So this only happen with right endpoint method. It can also work with left or midpoint.
Oh my God, it's like you flipped ahead to the back. Yes, you're gonna adjust this process for the midpoint method, the trapezoid method, and what might be the hardest of all, the left endpoint method. But that's in like 15 minutes.
You won't see the 50 minutes.
All right, are we good? So here's where things go a little cray-cray. If you, this is the setup. And if you get to the setup, it's like, check. When I looked on the AP exam, the new AP exam that they've released for AB and BC, getting to this point here, recognizing this on the multiple choice, is as far as you have to go. We are going for bonus innings here. This is the director's cut. Okay. I want to push you more. I want to figure out what this number actually is. I will not assess you on this, I promise. So just enjoy it for learning's sake. All right, so here we go. Gosh, I hope it fits on this board. All right, limit as n approaches, I'm for real. I equals 1 to n, we've got 2 over n times f of 2 plus 2 over n times I. The benefit of this problem is you know what f is. F is actually a function. And the function in this case is this 2x squared minus x plus 3. So everywhere I have an x, replace 2 plus 2 over n times I with that. And don't get all like, but I've got to take the limit. Yeah, eventually. Right now, I'm just bringing all the other stuff along for the ride. So what do I need to do? I need 2 times 2 plus 2 over ni squared. Minus, I need 2 plus 2 over ni plus 3. Is it video okay where this comes from? Anthony, you doing okay?
Yeah.
Okay. The reason that this all works is that in a perfect world, there are properties of sigma notation that you would have mastered in pre-calculus. The reality is, I don't think you did. Anthony, are you capturing what's over here on film?
Because I had it going there for a second.
Yeah, that's why I asked. Okay. All right, so everybody's good?
Yeah.
We're going to clean it up. We're going to do some legal math. So if you see legal math, go for the legal math. Legal math such as?
Distribute.
You want to distribute, Chepe, where do you want to distribute? You want to distribute the 2 through the parentheses there? Oh, see, I said legal math. Yes, legal.
Because it's squared, so you can't.
You'd have to square it before you multiply by the 2, but the squaring is wrong. So go square.
Oh.
You guys are like professional squarers.
No, we're not. That's what you
Okay, so you are probably doing a little box right now, right?
Yep.
Okay, so 2 over n times 2 plus 2 over n I times 2 plus 2 over n I is going to be 4 plus, I think, 8 over n I plus 4 over n squared I squared minus 2 plus 2 over n I plus 3. Look at me writing limit as n approaches infinity every step of the way. Bless.
Let me see.
Where? Oh.
After this, I get to do optimization for 2 periods with the AB students.
Oh,
I love being the smartest person in the room.
Break their hearts, Mr.
How are they doing?
I think he.
Really well.
What about those people in the flyings? They're gonna come back.
We got video for that.
Oh yeah, minus 2. Oh, it's on the last one.
Okay. So 2 plus 2 over ni, the whole thing squared gives me this. I distributed the 2. I distributed the subtraction sign. I combined my like terms where I had them. I distributed the 2 over n through. I have not done any calculus in these last 3 or 4 steps.
What?
It's just algebra. Big-brained algebra, but it's just algebra.
So how did an exponential function work for natural log?
Let's see.
Well beyond.
Oh, so
Well beyond what we
so
can
we're
do.
just focusing on polynomial functions.
We're going to focus on polynomials because they are nice properties.
Let's see.
Very nice properties.
What kind of great thing was?
That's just a great question. That was a really weak handshake, but it was a great question. Okay, is everybody okay with the algebra to get to
Yeah.
where we are?
Yeah.
Okay, even if you're not, just jump over to there. Okay,
Got it.
so the only thing standing between you and finishing this problem off is properties of sigma notation. Not calculus, pre-calculus. But sigma means, what does sigma mean? It means sum. It means to add up. And because I want you to think addition, that means you get nice properties of addition.
So then we're gonna take out that sigma part and put it on the
We're going to take this, we're going to sum these terms, sum these terms, sum those terms. So we're going to say, okay, no big deal. Limit as n approaches infinity, sigma 1 to n of 18 over n plus big sigma 1 to n, 28 over n squared I, plus big sigma, I goes from 1 to n, 16 over n cubed I squared. That's just a property of sigma notation. I'm adding, I'm going to distribute over addition. Then there was another strange property that I don't think you guys had ever seen before,
Not even pre-calc.
that you should have seen in pre-calculus, but
And then
We should,
something
but we
about how the number after the sigma goes to 4.
yes. There's something special. You've got variables here,
The constant.
and you have constants.
Yeah.
You forgot about this.
So you take out the constants and you put it in front of the sigma notation.
Okay. Because 18 is a constant, imagine you're summing up 18s, 18 times something, 18 times something, 18 times something. That 18 is a common factor, so that's the thing that you can factor out in front, right? So what are the constants here?
18 over n.
18 is a constant. 18's not changing. There's another constant
yeah.
here.
And
N. Why is n a constant? Why is n a constant? N kind of looks like a variable to me.
We're going to.
That's not mine. What's changing
Oh,
is I. This is your counter, right? You determined what n was in the beginning. I is what changes. I is 1, I is 2, I is 3, I is 4, I is 5. So all the constants you can pull out in front.
So, and it's some number.
N is a number. It is a fixed number at the beginning. We're going to do something with it in a little bit. So I've got to do 18 over n, big sigma. What's left over? 1. Plus, the next big sigma. What are the constants? What's the variable?
28 squared.
28 is a constant. 28 will not change. N squared is a constant. N squared will not change. I is the variable. 28 over n squared. I goes from 1 to n. I. And then we've got this last one here, and I'm sure you guys have figured out the pattern here. The 16 and the n cubed are constants. I goes from 1 to n of I squared. There's one more thing standing in your way. Okay. Not standing in Victoria's way, she's got her notes. The reason that sigma notation is so nice, there are properties, there are formulas that you would have studied back in pre-calculus that you remembered, or they're at the top of your handout. And one of them says that this guy here, if I'm summing 1 plus 1 again, plus 1 again, just plus 1 again is going to be, if I'm adding up 1 n times, what am I going to get?
N.
You're going to get n. So I've got 18 over n times n plus 28 over n squared. This next one you're not going to remember necessarily. But there's a formula here. Victoria, what's that formula? You've got it on the paper. If I'm summing I,
was it the n times n plus 1 over 2?
n times n plus 1 over 2. I am not expecting anyone to memorize it. This is not the thing I'm worried about. Do not memorize it. Plus 16 over n cubed. There's also a formula for summing the squares.
And that's n
Yeah.
times n plus 1
n times n plus 1.
times 2n plus 1 over
Is
6.
it all over 6?
Yeah.
Look at that. That guy there no longer requires sigma notation. If you said, what's going to be the sum with 100 rectangles, I wouldn't go through all this fun stuff again. All I would do is say, oh, you want 100 rectangles? I got your 100 rectangles right here. 18 divided by 100 times 100. Could I do that without a calculator? Of course you can do that without a calculator. 28 divided by 100 squared times 100 times 101 over 2. Given enough time, I can do this with a calculator. I can do all this without a calculator. That's what Riemann could do. And that would give you an exact answer? Why? Why an approximation?
Yeah, it makes sense to say approximation because you're going to limit
If I use 100 rectangles, this is an approximation because
you could use more rectangles.
I can use more rectangles. I can get a more accurate answer by taking the limit as the number of rectangles goes to infinity. So that's why this last step, but I've been writing it all along, all through this process, is go take the limit. Take the limit as n approaches infinity. What happens over here as n approaches infinity?
The ends cancel.
Don't those n's? Those n's cancel out? And so I'm going to write my answer up here. 18 plus, look over here, 28 over n squared times n plus 1 over 2.
You can cancel out an n.
I can definitely cancel out an n.
When it's safe in the bottom.
And I can reduce the 2
Oh,
to the
yeah.
28. That's going to give me 14. But look what's left. 14 times n plus 1 over n. There's something you guys know about limits. About infinite limits.
They're from the same degree, we just cancel them out. Just
The degree up here, this is degree 1. The degree in the denominator. Degree 1, you look at the ratio of their coefficients. The only thing that survived,
14.
14 in the numerator and a 1 in the denominator. So what's that limit? 14 plus, try that last one. N, that means n cubed when I multiply everything out, right? N cubed in the denominator. Degrees are the same.
So then you just have to simplify. 16.
So 16 over
6.
6. You guys all agree 16 over 6 is the coefficients? Brian looks like he doesn't agree. What about the 2? What do you think it's going to be?
Yeah.
So it's 32
If
over
you
6.
actually were to multiply this out and you focused on the coefficient of the biggest one, n times n plus 1 times 2n plus 1, the biggest one is going to be 2n cubed.
It's 32.
So it's 32n cubed over 6n cubed. So what you're going to get is 32 over 6, which is 32 plus 16 over 3, which I think is 112 over 3. Check it on your calculator. Let's do what Riemann couldn't have done at the end of this problem. Let's actually see, is all of this beautiful mathematics that makes me just want to jump up and down and
It
say,
is.
thank God I'm a math teacher.
It is right.
It is right. How do you know?
32 is 96 over 3.
Oh, no, son. That's not what I'm... Sorry. Sorry, you're focused on the wrong part there. You were focusing on is 32 plus 16 over 312 over 3. No. I'm asking,
Oh.
is this
Oh.
equal to 112 over 3?
Brian?
But you have a calculator. And you can definitely evaluate this on your calculator. Find your calculator. Find your calculator.
Calculator's like right there.
Go get it.
I can't reach.
No.
Hey, Roger.
Please tell me it's 112 over 3.
He's on the screen.
113 over
2
3.
to 4, right?
It's 111.
It's 37.33333.
It's 38.
It's not 38.
That's
112 over 3 is 37.333.
It's 111.
This is all thanks to Riemann.
You're welcome.
I hate you.
And he did
Yeah.
all of this with no calculators, nothing.
Let's
He
go.
was a man with an idea.
Very happy.
Yeah.
So who proved the second notations then?
That was, I think it was his mentor, Gauss was his mentor, I think? Or was it Bernoulli? I was doing a little bit of reading this morning. I think Gauss was his teacher. So, we can, Riemann depended on a really good, gifted teacher. Just like the 7 of you schmucks. All right. Keep in mind, the part that I really care about is here. Can we all set that up?
Yeah.
All the stuff after that, that's just the bonus innings because we're in Calculus BC and I want you to be able to show off for the ladies and the guys. What's that?
So, until where do you expect us to finish the problem?
Oh, that's good because Brian knows the answer to that. Where do I expect you to be able to get to? Here.
Oh, yeah.
Okay.
None of that. That's the point. This is the piece. This is the piece. This is just celebrating our mathematical brilliance. Brian.
Wait, but where'd you get the n times n plus 1 over 2?
The n times n plus 1 over 2 is a formula that works, that if you had a stronger background in sigma notation, you would just know.
Oh,
You would have memorized it.
Is this calculus 3?
No, this is Calc 2. Depending on the school, Calc 1. All right, so here's what I want you guys to do. You got about 11 minutes left. This is not the homework.
What is
There is no homework on this tonight. The homework that I want you to focus on are the 3 response questions from the trimester exam. I've got about 20 minutes blocked off tomorrow so we can talk about that. I'll take any and all of the questions. Here's what I think would be the right thing for you to do. See what you can do with questions 1, 2, and 3. And then I'm really interested in what you can do with this partner practice. Okay? I'm just gonna leave this up here to scare the E out of the ABCs.
That would be awesome.
That would be awesome.
No, video did me
January, guys. Memorize it.
Actually, it'll be right when we come back from Thanksgiving. All right, get to work.
Yes, remember this word.
Be like, taking notes. Sorry.
Oh, you can't.
Lucio.
They'd be surprised. I need paper. Is that good for you? Oh, it said use the calculator. Okay. I gotta go.
Did someone do that? Oh, so did you ready to finish them?
Yeah.
Oh, okay.
Back up. Make this so
There must be an extra copy of the notes.
put it in the right folder.
Thank you.
Oh yeah.
Yeah.
All that I'm asking for you guys to be able to do in this first set is go backwards.
Stop.
Okay? So is there any part of this that's familiar? So what does that 1 over n mean? The width. It's the width of each rectangle. So the 1 over n represents the width of each rectangle. How many rectangles are we talking about?
We don't know.
You actually, you do know.
And
That's what this, right, it's a matter of pulling all the pieces here. So you're summing from, I'm gonna have to erase it.
No, no, no. No.
No.
Put down the
Put it in
projector screen.
corner.
Put on the projector screen.
Oh, just put the projector down.
That's a good idea.
Made him a better man.
There we go, the third board. So I hope everybody at least recognizes that this is a definite integral question. Now, if it's a definite integral, you have to be able to tell me the limits of integration and the integrander. Okay. Is there any of that that you get from over here?
The width.
Okay, what's the width?
1 over n.
The width is 1 over n. Okay, that's a good start. What else? What else do we know? What else do we get from over there? I think you know the function. Look at what you're summing. Look at what you're summing. Your width is 1 over n. So that means if I is equal to 1, you've got 1 over n to the 4th power, plus 2 over n to the 4th, plus 3 over n to the 4th, plus 4 over n to the 4th power. This guy here is your function. So that means you're integrating x to the 4th with respect to x. If you think about your first term, where's that first term? Or what is that first term? If I is equal to 1, you've got 1 over n, right? The next term, 2 over n, 3 over n, 4 over n, all the way out to the last term, n over n. I'm using my counter. I is equal to 1, I is equal to 2, I is equal to 3. But 1 over n represents the width of each rectangle,
But
and you're using,
V over M.
I guess I didn't tell you that part. I should have.
Is this the right endpoint?
It's the right endpoint method.
So it's only right
So where are you starting?
one.
No, that's actually not where you're starting. The width of each rectangle is 1 over n. So you've got 1 over n times 1 over n to the 4th, 1 over n times 2 over n to the 4th, 1 over n times 3 over n to the 4th. You must be starting at 0. Because the width, the delta x, is 1 over n. So this is going to be the integral from 0 all the way out to my last one, which is 1, x to the 4th dx. And if you plug that into your calculator, and you get an answer, which you guys should all be able to do, you should get, I think it's 0.2. These I just want the setup.
Yeah.
So if you integrate from 0 to 1, x to the 4th with respect to x,
No, it's gonna be 0.8.
0.8.
That's what I did.
No, you got 0.2.
Yeah.
Okay, so let's make it right now.
All right, let's take a gander at the second one.
So another width is 3M.
Okay. So I'm doing a definite interval. The width of each rectangle is 3 over n. Usually the easy piece to see is the function. What's the function? The function usually is what's coming inside here in the sigma notation. This is how you're determining the height. So what's the function there?
Yeah, that's a power 4.
I've got 2 plus 3i over n to the 4th power.
That's to the power 4.
That's x to the power of 4.
Hmm?
Because that's what's being done to all this stuff here. Let's look at the endpoints. What's the first one? The first one is 2 plus 3 over n. That's what happens if I is equal to 1. What's the next one?
4
It starts at 2, doesn't it?
With I equals, yes. So if I is equal to 1, inside here you're going to have 2 plus 3 over n. If I is equal to 2, you're going to have 2 plus 6 over n. 2 plus 9 over n. All the way out to the last one. What's that last rectangle going to be?
2 plus N over M?
2 plus that last rectangle should be 3n over n. So what's that last endpoint?
3, 5. Right, plus 3N over M.
3n over n, which is 3 plus 2 is 5.
Oh, no. Oh,
This is
I thought
telling
that
me
too.
where my last rectangle ends. Where's the first rectangle?
At 2.
The first rectangle's at 2 because my width is 3 over n. So all this work here was just to get you your limits of integration, which is going to be from 2 to 5. See what you can do with the last one.
For the one that was 2 over 9 plus the one plus 2. Going from negative 1 to n, right endpoint method. Good. The width is going to be 2. So 2i over n.
And for midpoint, these two will just cancel out.
Oh, wait, no, lie.
So how would you consider that for midpoint?
So think about that first rectangle. You start at negative 1. The width is still 2 over n.
Oh, so it all doesn't matter how do you define it? Does it define it?
Okay, hold on. So we're doing a definite interval. What's the function?
Square root of
Square root of,
X squared? 1 minus x squared.
let's try 1 minus x
Yeah.
squared. The width of each rectangle is 1 over n. The first rectangle, the first x value would be what, 1 over n? Then it's 2 over n, 3 over n, dot, 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 dot. The last one is n over n, which is 1. The first one, which I'm not actually using because of the right endpoint method, is 0. And so I go from 0 to 1. Okay, hopefully we'll get a little bit more time to play around with this tomorrow. What I care about greatly is, can I give you the original definite interval, and can you